Hello, we continue with section 4, and this time we are going to study the phenomenon of diffraction. To study this phenomenon, we will make a small introduction of it. We will see situations in which it occurs, and then we will study or show consequences of everyday life in which the phenomenon of diffraction takes place. Let's start. And let's see what Jota is observing. Jota sees a wave front propagating. He encounters an obstacle. This obstacle is a small hole. And by the phenomenon of diffraction, which is the cause of this, he observes a wave front typical of a point source. Let's see what he observes now. Now what he observes is also a wave front. In this case, the hole is bigger. And what it observes on the other side is a wave front, similar to that of a plane wave. The difference between the two cases is the size of the hole. And let's see what Amanda tells us. Amanda tells us, she shows us that this is due to the phenomenon of diffraction. And this is the phenomenon whereby a wave is deflected as it passes through a hole or encounters an obstacle. It has to be fulfilled that the size of the aperture has to be of the same order of magnitude as the wavelength of the wave motion. That is what happened in the first case. That is why we clearly saw a wave front of 1 point source, while in the second case the ratio between the aperture and wavelength was not of the same order. Why did it look practically like the wavefront of a plane wave? Well, by Huygens' principle, it tells us that every point on the wavefront becomes a secondary wave. If it is only one point that propagates, we see that the wavefront is the one that Jay saw in the first simulation. As we go on, because all the points behave as secondary sources, we see that the wavefront is varying, and when we have a continuum, it is almost as if we had that of a plane wave. So in the second case, J, what he observed was a wavefront with some deformity, but similar to that of a plane wave. Why does it seem in some cases that the waves bend through the corners? We are all aware that there are times when passing cars we actually hear sounds, and it is usually the low sounds that we hear. Now we will see why. It is the same phenomenon that occurs when we see a light source without seeing the origin of that source. Let's approach the case of sound, but it is similar. Let's see. In this case, Jay is playing the drum, which emits a low sound, while Amanda is playing a flute. Which emits a higher pitched sound. What happens in these cases? Well, in the case of the drum, the wavelength is large, since the frequency is low, and in this case, it gives the sensation of bending the corners. Now we'll see what happens with Amanda. In Amanda's case, when she plays the flute, the sound is higher pitched. It is a higher frequency sound, and therefore the wavelength is shorter. What happens? Well, it seems that in this case the propagation is in a straight line. What happens is that the high frequencies are directional, and therefore they diffract less, while the low frequencies are omnidirectional, and therefore a citizen in an adjacent street would hear how Jay is playing the drum, while he would not be able to hear it when Amanda is playing the flute. What have we seen on this lesson? On this occasion, we have studied the phenomenon of diffraction, and we have seen that it is clearly observable when the size of the obstacle is of the same order as the magnitude of the wavelength. We have particularized for sound waves, seeing that low-frequency sounds are more omnidirectional because they have a lower frequency, while high-frequency sounds, for example from the flute, are very directional. That's all. See you in the next lesson.